propagation. This is kind of where the rubber meets the road. And I'll turn it over to him.
Can you hear me now?
Yes, sir.
Well, thank you very much. I'm excited to be here. I've been in ham radio for about 7 years. I started when I was kind of an old guy, and I'm still an old guy. So, I mostly do DX and contesting to get DX. And so, is that feedback? Or?
It sounds like it is a little bit. You want to trade to this one?
No, I'm all right. If we can you hear me still?
Yes.
Get this down a little lower. Does that work? Can you still hear me in the back? Okay, thanks. Propagation, well, this is my definition of propagation, is the ability to move radio signals far beyond the normal length of its initial output. And there's a lot to talk about in propagation. It's a never-ending learning experience. I mean, you can learn and learn and learn about propagation and the do's and don'ts, and then as you'll see later on in the presentation, some of the things you learn aren't really true. And some of the things we think we learn aren't true. So we know what we think we know, and it changes all the time. But propagation is important if you're concerned about working long distance. DX is long distance, and that's what we're trying. It doesn't matter whether you're trying to work long distance with 2 meters or 6 meters or 10 through 160 meters. Propagation is important, and if you're interested in working DX, and generally I'm going to be talking about working outside the United States, probably outside the continental of North America, it's important to understand propagation. There's a really lot of stuff I'm going to cover today, a lot of details, way too much information probably for even a presentation. But the good news is Matt has agreed to take this PowerPoint and put it up on the website so you can go back and review it at your leisure. And feel free to look me up and give me a call or email me. I'll be glad to answer the questions I can for you. First of all, let me go over some definitions real quick that we're going to be running into that's important for you to understand. First one being absorption. Absorption is when a layer is not effective at propagating data. In other words, it's like a sponge. It sucks up our radio waves and it doesn't go beyond the layer. Ducting is like a pipe where a radio signal will go out and it's just like going through a pipe out to a direction. It really helps allow signals to go long distances. Scatter, you probably heard of 6 meter meteor scatter and stuff like that, where it bounces radio waves back there, and it's very good, especially during these meteor showers when we have. Ground wave is when the signal actually just traveling along the ground. Citizen band was a good example of ground wave, but then many of you remember what citizen band still does, will propagate out across the United States, even though it's only supposed to go 5 or 10 miles. But skywave is when a signal goes out and is reflected back off of the ionosphere, back to the Earth, and skip is when it reflects back up again another time. Okay, first of all I want to talk about the ionosphere. The ionosphere is the Earth's atmosphere. It's from the surface of the Earth up about 80 to 300 miles above the surface. It provides nearly all of our HF communications. The sun shining on the ionosphere changes the composition and height of the propagation characteristics. Here's a little picture of the Earth, basically this combines the ionosphere. We've got the Earth, the troposphere, what we call the D region, which I'm going to talk about each of these regions in a minute. Above that is the F region, E region, the F1 region, the F2 region. The troposphere is the Earth's atmosphere just above the Earth's surface and below the ionosphere. It contains about 80% of the ionosphere's mass and 99% of the moisture. It provides the reflection or reflections of radio frequency waves from temperature and moisture. Here's an example of showing a transmitting station going up, hitting the troposphere, skips back down to the Earth, back up the troposphere, and eventually getting over to the receiving station. How wide these skips are depends on the frequency you're working and the conditions of the ionosphere. The D layer is the lowest layer. It is not very useful for ham radio. During daylight hours, it absorbs most of the energy for the low bands. Everything below 7 megahertz. At nighttime, it totally disappears and makes the low bands usable. And when the sun comes up, it starts getting ionized again and immediately loses its energy after sundown. It does nothing in the way of reflecting signals. The E layer is seldom useful for HF. It acts very similar to the D layer. It can be used for E-skip on VHF. Here in the daytime, gone at night. The F1 layer has similar properties. Sporadic E, these are regions that are highly reflective, may last a few minutes or a few hours. If anybody works sporadic E, 6 meters or something, how long is the signal good? You don't do a long sideband conversation on sporadic E, I can tell you that. You're lucky to get the exchange back and forth because it comes and goes. Mostly for 2 meters and 6 meters. And the highest activity is in early summer and winter. The F layer, in the daytime, it divides up into 2 layers, the F1 and the F2 layer. F2 layer is on top, it's closest to the sun, it gets the most ionization of the UV and X-ray energy. And at night time, the F1 layer loses its energy and becomes slowly absorbed into the F2 layer and stays there right until sun up in the morning. With the F2 layer, you can get a single bounce up to 2,500 miles on long path communication. It literally will go all the way around the world. The F1 region ionization is always the greatest when the sun is directly overhead. The F region, the summer propagation, the F region in the summer, the propagation is best. And in the winter, it's least. Here's another example of the layers. Here's F2, F1, E, D. And this is where the sun's shining right here. And then you can see as the sun goes away, these slowly start disappearing. And then it all becomes absorbed into what's called just the F layer at night. The F layer is the multi-hop layer. This is where propagation hops from the ionosphere to the ground, hopefully back up and continues on. Most communications are beyond 2,500 miles. Each hop involves attenuation and absorption. And I'll explain that in a little more detail in a second. The longest signal that reaches the receiving station will be the weakest. Because it's just like throwing a ball up in the air. The first time it bounces quite high, and then the next time it's lower and lower and lower and lower until it finally disappears. And this is the same thing that's happened with skip around the world. Sometimes we get what's called a chordal hop, which is like a pipeline out that has low attenuation and the signal will just really take off. But those things come and go. I mean, it's really hard to predict them. Here's another example of those skips. You can see it's getting lower and lower and lower and finally released at the receiving station. What is this? Yes and no.